Hey everyone, welcome back. This explainer is brought to you by Forge College. Now, if you were with us for our last lesson on scoping infrastructure requirements, you know we spent a lot of time in the abstract, sketching out operational targets, defining service-level objectives, and looking at expected request volumes. But today we're taking those blueprints off the drafting table and bringing them into reality. We are moving from that abstract scoping phase to concrete, deployable infrastructure blueprints for your Web3 environments, specifically for Solana and Ethereum node setups. It's time to actually build the machine.
So here's how we're going to build out this infrastructure. We'll start by looking at how our scoping targets translate directly into our setup. Then we'll meet the specific node roles, choose our topology, walk through a real-world proxy example, and finally wrap up with how to monitor the whole shebang. Right, let's jump straight into part 1, from scope to setup, turning our SLOs into blueprints.
We're kicking things off by bringing back those operational targets we established earlier. Why? Well, because you can't just throw servers at a wall and hope they stick, right? The constraints from our scoping phase strictly dictate our infrastructure choices. We essentially have this short list of absolute non-negotiables. We need predictable tail latency for our public reads, meaning our users shouldn't be experiencing any random lag spikes. We need strong isolation for our write endpoints so heavy reads don't block our transactions, and we need the ability to independently scale indexer back to queries. Because, let's face it, looking up a 5-year-old transaction takes a heck of a lot more horsepower than just checking a current balance.
Moving on to part 2, let's meet the node roles, or as I like to call them, the kitchen staff of Web3.
To really make sense of the node roles we need, let's have a little fun and imagine our complex Web3 architecture as a fast-paced, high-end restaurant kitchen. Just like a restaurant, if everyone tries to do every single job, you end up with burned food and angry customers. We absolutely need specialization. First up, the RPC front ends. Think of these as your waitstaff. They're out on the floor, they're moving fast, taking orders, and dealing with demanding customers. They handle short-lived, latency-sensitive requests. They validate the request, check the cache, and route it where it needs to go. And the absolute beauty of the waitstaff is that they don't retain any state. They are completely ephemeral. If the dinner rush gets crazy, you just horizontally scale. Bring in more waitstaff. If one drops a tray, another steps right in. They fail fast and they're auto-replaced.
Then, back in the kitchen, you've got the consensus or validator nodes. These are your head chefs. They are doing the absolute heaviest lifting, participating in block production, maintaining peer connectivity, and holding the canonical state of the blockchain. And because they're doing such critical, highly focused work, they require incredibly stable I/O capacity. They absolutely cannot be distracted by a flood of public read requests. If you mix heavy public load directly onto these consensus nodes, you risk pushing them entirely out of their consensus pace, and boom, the whole restaurant grinds to a halt.
Finally, we have the indexer and archive nodes. These folks are your back-office accountants. They handle the heavy analytic queries, historical state lookups, and massive data backfills. They're basically combing through 5 years of historical receipts. This is incredibly CPU and disk-heavy work. But, unlike the waitstaff, they can actually tolerate slightly higher latencies. The golden rule here? Keep the accountants entirely separate from the dinner rush. You derive their state via an ingestion pipeline, so they don't cavitate the resources of your chefs or your waitstaff.
Okay, part 3, choosing your topology. It's time to design the restaurant layout.
Now that we know exactly who our staff is, let's design that layout, what we call our architectural topology. Just look at how these patterns map to our requirements. First, you have the single-tier direct setup. Think of this as a simple food cart. It's operationally super simple, but the isolation for writes is pretty poor. You really only use this if your read volume is very, very low. Then, sitting in the middle, you've got the tiered proxy. This one's absolutely perfect for high read volumes where you need tight latency. And finally, the split stack setup. This is your Michelin star fine dining experience. It separates everything onto dedicated machines, giving you excellent isolation for writes and analytics, but yeah, it's definitely the most complex to actually run.
Let's see how this builds out specifically for the tiered proxy, since honestly, it's highly recommended for most scalable Web3 apps. Step 1, the user request comes in. Step 2, it hits an edge cache. This is a lightweight front end that immediately answers the easy, repetitive questions. And only if the cache doesn't know the answer do we move to step 3, the Origin RPC node. Doing it this way dramatically reduces the load on your origin node so they don't get completely overwhelmed by repetitive public reads.
All right, part 4, the real-world proxy example. Let's look at the actual blueprints.
Enough theory. Let's grab our technical pen and draw out a real-world scenario using the exact numbers we scoped in our previous lesson. Our restaurant is under heavy load. We are requiring our system to serve 4,000 public reads per second, and we've got a strict latency target. 99% of those reads must be served in 250 milliseconds or less. At the exact same time, we have 50 authenticated writes per second that need absolute isolation, plus 200 historical queries chewing up disk space. We literally cannot miss a beat.
To solve this kind of heavy load, we use a proxy, like Nginx, at the load balancer level to explicitly split our traffic into two distinct pools, an RPC public pool and an RPC write pool. The public pool handles the 4,000 reads per second, heavily assisted by that edge cache we just talked about. And the write pool? That's a dedicated set of back-end nodes that strictly process those 50 transactions per second. They never, ever cross paths. Write traffic never competes with the public read rush.
And to actually make that happen, you use a configuration block just like this one. This single, elegant routing role is basically the magic bouncer for our club. It looks at the incoming request, sees that it's targeting the /write endpoint, enforces the authorization header, and then passes it strictly to the isolated write pool. This is exactly how you operationalize that abstract write isolation requirement from your scoping document into cold, hard infrastructure code.
Which brings us to part 5, monitoring and next steps, keeping the kitchen running.
So, you've built the ultimate kitchen, you've hired the best staff, and you've got your bouncer at the door. But how do you know if everything is actually running smoothly before the customers start complaining? Well, you have to monitor your essential touchpoints. And these aren't just random metrics, they map directly to our node roles. You monitor front-end P99 latency to make sure the waitstaff is fast. You check origin CPU and disk I/O. You monitor validator block processing time to ensure the head chefs are keeping pace. You track index or ingestion lag for the accountants. And you watch your cache hit ratio to make sure your edge layer is actually doing its job. These specific touchpoints are the critical boundaries that dictate your alert thresholds and trigger your failover playbooks.
But look, hardware fails. It's just inevitable. So I want to leave you with this question. When a failure hits one of these touchpoints, how will your application's connection logic respond? Does it retry? Does it gracefully degrade? We are going to answer exactly that in our next explainer on RPC connection strategies. Until then, thank you so much for learning with us today. And remember, to master more Web3 infrastructure concepts just like this, be sure to visit forge.college. I highly recommend checking out their complete resources. Keep building, and I'll catch you in the next explainer.